Okay, this is part 2 of the IM1 Spring Final Exam Study Guide. So we're walking through it. We left off here. I didn't really talk about how to do 52 and 53, so let's start with that. I'm actually going to start with 53 here. I have the square root of 108, and 108 is not a perfect square. If it was, like if I said, what's the square root of, like this one here, 64, it's 8, because 8 times 8 is 64. What's the square root of 121? It's 11. But 108, I can't do that. So I need to think about all my perfect squares. Remember, our perfect squares are, well, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16. And I could keep going as far as we need to. Blah, blah, blah. But we want the biggest number in that list that's a factor of 108, and that happens to be 36. Like, we don't want to just factor 108 any way we want. We could have said it's 2 times 54, but neither of those are perfect squares either, so we'd be in the same situation. But here, if we factor it this way, in the real number system, we can square root each factor separately if we have the square root of a product. So the square root of 36, we know that it's just 6. But the square root of 3, we can't do anything else with that, so it stays the square root of 3. In the back of our minds, we should be checking to make sure that 3 doesn't have another perfect square. Maybe we made a mistake and didn't get the largest perfect square that's a factor of 108. It doesn't mean we're wrong, it just means we can bring out more. So if 3 could factor further as a perfect square times something else, then we could keep going, but that's as far as we can go. 3 doesn't factor any further. Now let's go back to 52. It's the same idea, but when you have the square root of a fraction, just like you can square root 2 factors of a product separately, you can square root the numerator and denominator of a fraction separately. So the square root of 1, well, what times 1 gives us 1? It's just 1. But the square root of 28, that's not a perfect square. So again, thinking of all of our perfect squares, 1, 4, 9, 16, 25, and so on, the biggest number in that list that's a factor of 28 happens to be 4. The square root of 4 is 2, and 7 just stays in the square root. We can't bring out any more perfect squares from 7. All right, check your work on 54. Same idea, the biggest perfect square that's a factor of 75 is 25. The biggest perfect square that's a factor of 63 is 9. We evaluate those square roots of perfect squares, so the square root of 25 is 5, the square root of 9 is 3, but these factors can't be square rooted nicely, they just stay inside the radical symbol. All right, 55. Evaluate the following exponential expression. We have negative 8 inside parentheses, so we're actually including that negative sign in the base that's raised to the power of 4/3. So we know that when we have a fraction in the exponent, we can write it in radical form, and I can do that cubed root first or exponentiate to the 4th power first, either way. Usually it saves us a little bit of work if we're doing it mentally to do the cubed root before we raise it to the 4th power. So inside the parentheses here, the cubed root of negative 8, what number times itself again gives us negative 8? Well, that would be negative 2, because negative 2 times negative 2 is positive 4, and positive 4 times a third negative 2 would be negative 8. All that's left is to take this negative 2 and raise it to the 4th power. Negative 2 to the 4th power would be positive 16. Here's 56. Same idea. You could write a little 2 in the index, but when it's a square root, it's implied, so we don't have to write it. That's just 2. The square root of 4 is 2. All right. So for the following problems, we have a function h. It is exponential. It tells us that, and that means it's in this form. H of x is a times r to the x, where a is our initial value, or our starting point, our y-intercept, and r is our, well, sometimes it's called the factor. It could be a growth factor or a decay factor. Sometimes it's called the common ratio. It's the thing you're multiplying by to get from one term to the next. So as long as you remember, exponential functions are a times r to the x. Well, what's a? It's 1. What's r? It's 4. 59, evaluate h of negative 2. So that means take this function and plug in negative 2 everywhere you see an x. So I still have a 1 times 4. It was to the x power, but I'm replacing x with negative 2. And 4 to the negative 2 power, because of our negative exponent rule, I can do the reciprocal of 4 to the positive 2 power. And 1/4 squared, 1/4 times 1/4 is 1/16. And 1 times 1/16 is just 1/16. So I tend to leave my answers as fractions. If you happen to write it as a decimal, it would be 0.0625. All right, we have a diagram. This is from our chapter 8. We have figure DEFC, and we are doing some rigid transformation to get figure RQTS. What's the image of F? Well, F is that obtuse angle. It matches up with S. So I'm just asking you to pair up corresponding parts of the pre-image and the image. FC is this short side here. The short side here would be ST. Number 62, we have a triangle ABC, and we need to translate, that's what that capital T stands for, 5 units to the left, 2 units up. Be careful, the boxes are scaled by 2s, not 1s. So if I go 5 units to the left of, like, let's say point C here, that's 1, 2, 3, 4, 5. And then 2 units up, 1, 2, would put us right here. If you do the same thing for A and the same thing for B, you have all 3 points of your image. Connect the dots, draw your triangle. They should look congruent, the 2 triangles. All right. For 63, find the image of C when we translate it 4 units to the right and 5 units up. So start at C, go 4 units to the right, 5 units up. Again, it's scaled by 2s. We'd be on point E. Number 64, how can we translate point B to point E? Well, they have the same x-coordinate of -3, so we don't need to move left or right. We just need to move up. If you count it, that's 2, 4, 6, 8, 10, 12, 14, 15. We have to go up 15 units, so that's why we have this rule here. Number 65. We have the vertices of a rectangle. I don't give you the picture, but you can graph it if you want, or just picture it in your head. These 4 corners, if we plotted them on a graph, they would make a rectangle. And we're going to do some translation. It doesn't tell us what translation, but that translation maps R, that's this one here, -5, -5, to the point -4, 2. What is the translation? And then what's the image of U? So what do we have to do to the x-coordinate, -5, in the pre-image, to get the new x-coordinate in the image, -4? Well, -5, if I add 1, I'll get -4. So I'm adding 1 to the x-coordinate, and then we need to look at the y-coordinate also. So the y-coordinate of R, the pre-image, is -5, and the y-coordinate of the image is 2. So what do we have to add to -5 to get 2? Well, we have to add 7. So the translation that we are performing is sliding R right 1 unit and up 7 units. That's the translation. I wrote it right here, or actually it's also here. And then we have to find the image of U. Remember, U is at -5, 1. So if we move that point right 1 unit and up 7 units, we would end up at this point U prime, -4, 8. Number 66, describe this translation. Well, that's right 3 and up 8. 67, if I move 5 units left and 1 unit up, how would we write that rule? You could write it algebraically like this. Subtract 5 from the x-coordinate, add 1 to the y-coordinate, or just put capital T for translation, -5, 1. 68. You should have this rule in your note card. If I rotate a point 270 degrees about the origin, that means that point, whatever it is, x comma y, is going to get sent to the point y comma negative x. And this negative doesn't necessarily mean that the number will be negative. It just means the opposite of the x coordinate. So if my x coordinate originally was negative, then negative x would be the opposite of a negative and it would be positive. But in this case, x is 30, so the opposite of x would go here. The opposite of 30 is negative 30, and y is 0, so 0 goes here instead. So 30 comma 0 would get sent to the point 0 comma negative 30. All right, if I reflect point J, that's this point right here, in line M, or that just means I reflect it over the line M, it would get sent to L. For number 70, please make sure your scale factor is the image length, the ones with primes, divided by the pre-image length. It's 6 divided by 3 and not the other way around. A common mistake I see sometimes is people will have 3 over 6 instead and say the scale factor is 1/2. Just make sure you don't confuse your image and pre-image. All right, 71, we have vertical angles. Vertical angles are congruent, so we can set these measures, 4x minus 80 and 6x minus 40, set those equal to each other, and then solve for x. I did the same thing to both sides, so my equation stays balanced. That's allowed. And when I combine my like terms, I'll get 2x equals negative 40. Dividing both sides by 2, I'll find that x is negative 20. These are complementary angles. They tell us that AOC is a 90-degree angle, a right angle. So 74 plus something is 90. That something is 16. So the measure of angle BOC is 16 degrees. 73. It's a similar idea, but instead of complementary angles in 72, we're now looking at supplementary angles. They add to 180 degrees. So 144 plus something is 180. That should be 36 degrees. 73, they tell us the measure of angle AOC, the entire thing, is 163 degrees. But it's broken into 2 parts. They tell us AOB is 3x plus 90. We don't know what x is yet. And BOC, this one here in red, is 6x plus 19. So this is called the angle addition postulate. I can add these 2 parts, the green part and the red part, and it's going to equal the measure of the entire thing, the blue part. So combine our like terms, we'll get 9x plus 109 is 163. And we work on getting x by itself. We should find that x is 6, but be careful, it doesn't say solve for x. It says find the measure of angle AOB. So now that we did all this work and we know x is 6, we can plug 6 into our expression here for measure angle AOB. So 3 times 6 plus 90 is going to be 18 plus 90. That means the measure of angle AOB, this one here, is going to be 108 degrees. 75, same thing, we're going to solve for x and then use that to plug in to get our answer. So the green part plus the red part should equal 180. It's a straight angle. Solve for x, plug in your value for x to find the measure of angle MON. So 6 times negative 6 plus 138 should be 102 degrees. So we've got 102 degrees here. 76, we have parallel lines cut by a transversal, and these 2 angles are both in the upper left of their respective intersections. So they're called corresponding angles. Those are congruent when we have parallel lines, so we can set them equal to each other, solve for x. We'll get x as 20. And again, when you have these parallel lines cut by a transversal, you end up getting 8 different angles. 4 of them are congruent, and the other 4 are also congruent. And if you get So like these yellow ones are all congruent, these blue ones are all congruent, and if you pick one yellow and one blue one, they will be supplementary. So if we want the measure of angle 6, that's a blue one. This yellow one is 136. So 136 and the measure of angle 6, those are going to add up to 180. Solve for the measure of angle 6, you should get 44 degrees. Same thing here, we're given that all the yellow ones are 25. So if we want the measure of angle G, well, hey, that's a yellow one, so the measure of angle G is 25 degrees. 79, we have alternate interior angles. Those are congruent. So set those equal to each other, solve for x. We should get 41. 80, it says find the value of k. And we know nothing about the sides of this triangle. We just know one angle is 33 degrees, one angle is 75 degrees. We need to find the third angle. Well, it works out because we know that the three angles have to add up to 180. So 33 plus 75 is 108. So 108 plus what is 180? The answer is 72. 81, we're going to use that same idea that three angles in a triangle add up to 180. But we actually have three different triangles here. We have this blue one, we have this yellow one, and I'm not sure if we'll use it, but we also have the whole thing. Starting with the blue triangle, we know two angles, find the third, just like we did in the last problem, and we'll get that x is 76 degrees. But after that, x and z, they make a straight angle. They add up to 180. But now that we know what 76 is, we can find z, subtract 76 from both sides, z is going to be 104 degrees. Then we look at the yellow triangle, and again, we know 13 degrees, we know 104. Find the third one, should be 63. 82, we have vertical angles here. So that's 110, and then it's the same problem as before. You know, two angles in a triangle, find the third. It's 13. 83, we have triangle ABC, and we reflect it over the line y equals -2. I drew that line here as a red dotted line. The first question we have is, would the new triangle be congruent? And right off the bat, if we're reflecting, then yes. Reflections are rigid transformations. They preserve congruence. So A prime, B prime, C prime will be congruent to ABC. But it also asks us, what would the coordinates of A prime, B prime, C prime be? And that's the whole reason I drew the line of reflection. Corresponding points like A and A prime, or B and B prime, or C and C prime, those are going to be the same distance away from the line of reflection, just in opposite directions. So A is 1, 2, 3 units above the line of reflection, so A prime will be 1, 2, 3 units away as well, just below. C is 1 unit below the line of reflection, so C prime will also be 1 unit away, but this time above the line. Now B is on the line, it's 0 units away, and the opposite of 0 is 0, so B prime is also going to be 0 units away from the line of reflection. B won't move at all. And using that, we can look at the graph, and those would be the coordinates of A prime, B prime, and C prime. Here's 84. We have triangle ABC and triangle A prime, B prime, C prime. It asks, what kind of transformation is it? If you're a visual person, you might have seen this reflection, or it might have looked kind of like a 180-degree rotation to you. And there is a way that you could rotate this triangle and get the same looking triangle, but it would be labeled differently if it was a rotation. If it really was a rotation, let's, here, I'll draw it kind of the same way. A, B, C. Now, if I take that pink triangle that I wanted to rotate, if I rotated it 180 degrees, it would end up over here. But do you notice that A and it doesn't match up with where A should go, right? That's a C, or C prime. And same thing here, C doesn't match up. This should be C prime, and it's not. So because of the way our image is labeled, with A prime being here and not here, and same for C prime, This is not a rotation, this is a reflection. Go ahead and pause the video, you can read this if you want. Number 85. We have two triangles that we know are congruent, and QS and TV are corresponding parts of those two congruent triangles. I don't even need the picture, but if it helps, you can draw it. I know they're corresponding because Q and S are the first and third letter, and T and V are also the first and third letter. So they've got to be corresponding parts. And I know that corresponding parts of congruent triangles are congruent. So these have to have the same length. So I can set those lengths equal to each other and solve for V. It's not asking us to solve for V though. It's saying find the length of QS or TV. So plug this into V and get a length of 8. You could have also, just as a side note, you could have plugged 2 in for V here, and you will still get 8 because that's the whole point. These sides of the two triangles are congruent to each other. They have the same length. 86. The two triangles are congruent as suggested by their appearance. Find the value of G. Okay, so if these two triangles are congruent as they appear to be, then this longest side of the first triangle should be congruent to this longest side of the second triangle. And the second triangle, that side is 17 units long, so G is 17. 87. I highly recommend you mark up your picture. It wasn't actually written on here, but if it's given, any information that you know, like RS is congruent to UT, that means we know these two are congruent. And in the same way, since RT is congruent to US, mark that as well. They state that in lines 1 and 2 of our 2-column proof. The third thing says that ST is congruent to TS. Well, wait a minute, that's the same line segment. So anytime you're saying that something is congruent to itself, that's the reflexive property. If you want to write it shorthand, I'm not even checking to see if you say it's the reflexive property of line segment congruence or the reflexive property of angle congruence. If you say the reflexive property, that's good enough. So this proof ends by saying that triangle RST is congruent to triangle UTS. So looking at our picture, because we made these nice tick marks, we can see that we have one pair of congruent sides, a second pair of congruent sides, and a third pair of congruent sides. So this is the side congruence postulate. If you just write side, that's okay too. 88. What other transformation do you need in order to prove the triangle's congruent using side angle side? So we already know that BC is congruent to CD. But then we have another reflexive property that we kind of like we used in the last problem. So I could say AC is congruent to itself. That's this part here. So we have two pairs of sides, and remember, anytime you have two pairs of sides, we have to watch out because side angle side proves congruence, but side angle does not. Actually, there's a typo in here. There's no or. It's asking us to prove it this way. So we need to know that this angle is congruent to this angle in order to have side angle side. Cool. 89. Which triangles are congruent by angle side angle? Notice we have, actually that one is extra information. We don't actually need to know that AB is congruent to HG, but we do have angle side angle. So those two triangles would be congruent by angle side angle. Number 90, can we conclude that the two triangles here are congruent? Be careful, it looks like an angle trick, But these two triangles share side DF. So we can use that reflexive property, and then you can choose these two angles and the side and say angle, side, angle, or you could choose these two angles and say angle, angle, side. Either one of them would prove that the two triangles are congruent. Number 91, fill in the blanks. We write down the given information first. So these two sides are congruent. These two angles are congruent. Then line 3, we use that reflexive property. That line segment is congruent to itself. So we have side, angle, side, and side, angle, side. That's the reason for line 4. But then they say, okay, well, BD is congruent to DC. And there's no markings that tell us that's true, but we can conclude that because we just proved that ABD is congruent to ACD. And if the two triangles are congruent, then any corresponding parts of those two triangles have to be congruent. Number 92. The triangle is isosceles because it has two sides with the same length. But we know from the isosceles triangle theorem that the base angles have to be congruent in any isosceles triangle. So we're going to say that, well, if this angle is x, then this angle is also x. The three angles in a triangle add up to 180, so we can set up our equation here. Combine our like terms, x plus x is 2x, and then get x by itself. You can subtract 38 from both sides to get our next line. Divide both sides by 2, and you should get that x is 71. And you can check your work. 71 plus 38 is, in fact, 180. Got another isosceles triangle theorem here. We have two sides that are congruent. So if this is 56, the other base angle must be 56. So we've got 112 plus our third angle, x has to be 180. So x is 68. Number 94, the legs of an isosceles triangle have these lengths. So one side is x plus 1, the other leg is negative x plus 7. There was a typo here, so if you didn't change it in class like I asked you, please put a negative in front of that 3x, and then we can continue. What is the length of the base? Because we know the base has length negative 3x minus 3. Well, first of all, the legs have to have the same length, so we can set the length of the first leg equal to the length of the second leg. These two have to be equal. If we solve for x, we'll find that x is negative 3. We take that negative 3 and plug it in to the expression for the base. So negative 3 times x, well, that's negative 3 times negative 3. That'll be 9. Minus 3 will be 6. So the length of the base is 6. And our last one, number 95, find the values of x and y. So we have our picture here. It tells us that BAD, angle y, is congruent to CAD. We also have that these two sides are congruent, which makes triangle ABC isosceles. So I have an isosceles triangle, and then I also have a line segment from the top of the vertex of the isosceles triangle down to the opposite side, and that line segment bisects or cuts in half the vertex angle A. So that meets the criteria of our vertex angle bisector theorem. It means that theorem says that AD has to be a right angle or perpendicular to BC. And it also means that BD and CD are congruent. So because of that vertex angle bisector theorem, and we know that it's perpendicular, x has to be a 90-degree angle. And then we can look at this triangle here. Actually, I should take one step back. Since the whole thing is an isosceles triangle, we know that angle B must also be 46 degrees. And then the three angles in this triangle here add up to 180. So 46 plus 90 plus something is 180, and that something is 44. And that is it. That's the end of our final exam study guide. Reach out if you have any questions, and I will see you all for the final.